Here I am. What do you got for me?
I was wondering if we could go back over the publication biases and like that kind of stuff. This is a long time ago. I get hacking. The ones are so fun.
P-hacking and the other ones. Okay, so publication bias is basically just a tendency for journals to want to publish information that, that finds an effect of something, and to a lesser, or maybe not to a lesser extent, to publish findings that are interesting, that are going to get readers. So just like any magazine, I mean, if you go to the magazines, what are the magazines? If you go to the magazines, actually a magazine, it's a term for a store, right? Yeah, so you go to the magazine, and what magazines do they have up the front of the magazine? You got like People, Us Weekly, all this stuff, Men's Health, Women's Health, Cosmo, whatever. And they're all competing for business, right? They all want your dollars. And journals are no exception to this. They want people to subscribe to their journals and to buy their journals. And go online and you want to find an article that you're going to review for a class, and if your institution doesn't have the article and you don't have the time to wait for an interlibrary loan or something, you have to go buy it online. A single article can be like $25 or more. It's nuts. But anyway, so if a journal is publishing interesting results that are significant, then that journal is going to be more prestigious. So there's something called impact factor. And journals with high impact factor are subscribed to by more institutions, and they're seen as more reputable oftentimes. So there's this bias to publish things that are going to increase their impact factor. And novel, new, exciting results are something that can increase a journal's impact. And also, publishing things that, oh, we found an effect of something that's more interesting than, oh, here's something no one found anything. So there's this bias to publish interesting and significant effects, right? And so this can lead to a number of things that, given the publish or perish environment of higher academia, in which if you're not publishing, you're not communicating your results, you might not keep your job, this can create some pressures for individual researchers to engage in some ethically questionable activities, right? So p-hacking is basically when you maybe repeatedly analyze your data in different ways, looking for one analysis that's going to give you a p of less than 0.05. Maybe you take out some variable, or you include some control variable, or you add a couple more participants. The whole idea is that you are looking at your data, you didn't find anything, let's go back and look at it another way, let's go back and look at it another way, and trying to do things in order to find a significant result somewhere so you can potentially publish it. What other types of things were you?
File drawer effect.
The file drawer effect. Yeah, okay. So the file drawer effect is basically an individual does research in some area and they don't find an effect. Maybe someone else has published there's an effect of something. I read one of my friends on Facebook, he's really into like homeopathy and a lot of pseudoscientific stuff. And one video that he posted was presented by a guy who'd done some research to find out if people are aware when other people look at them. So he did an experiment in which people were looking at the backs of individuals' heads, and the individual had to the individual at whom they were looking had to indicate whether or not they thought they were being looked at. So this individual found a significant effect, and so, oh wow, people are aware that others are looking at them. How does this work? Anyway, a number of other people have tried to replicate this. However, they haven't. So this suggests that potentially this effect that this one individual found was just one of those alpha errors, right? Just by chance they happened to get this one. And it's possible that this individual had run a whole bunch of studies and found the one that came out right and published that. I'm not saying that he did or not, but that's certainly possible. So anyway, if this had occurred and no one who has done follow-up research on this individual's initial effect were able to get their null results published, right? Because they're all basically finding, oh yeah, there's no effect, no effect. Then this would mean that in the literature, the only stuff that's out there is suggesting that this is real. when in fact there would be a lot of evidence collected suggesting that it's not real, but it hasn't been published, so it just remains in someone's file drawer, or their thumb drive, or hard drive, or something like that. Does that make sense? Is there anything else about the publication bias stuff?
That's all of them.
You have something for me, Josie?
Oh, no. Well, I was wondering if there would be a study guide at all for the test.
No. Study guide, if you want to make one really easily, I would go through the readings and look for the bolded terms. In this most recent reading, I'm changing how things are formatted a little bit different, so there's not that ugly box around the links. Instead, the links will just be blue, like links are on the internet. And so the links, some of them are bolded, some of them are not. The links that are bolded, those are the ones that you should know. So you could create a study guide. Also things that have section headings. So like what are the different scale variables, ordinal, nominal, ratio, interval, that type of thing, where I've made some clear distinction between elements or have them in a list. That's a good way to identify the things that I'm likely to test from. I'm lazy like most people, and laziness is great. It's given us the microwave and the wheel. And if you think about me writing the test as lazily as I can, how do I do this? Well, I look for a list. And then I ask a question about the items on that list that will have you differentiate between those. And I might even ask you about that list a couple times. Speaking of which, if I do ask you a question, let's say about different types of variables, and I give you 4 choices, independent, dependent, extraneous, and confounding. Let's say that extraneous is the correct answer for the first question using that set. And then I go out and ask you another question. It's possible that extraneous could also be the correct answer for the second question as well. A lot of people think like, oh, well, he's not going to repeat the same answer twice. Most of the time, that's true, but it's not always true. So you should always go with the best answer. Speaking of the best answer, if you disagree with me about which answer is best, I'm always open to discuss things. Occasionally, sometimes when I make the test online, or even in a physical copy, I mess up the key. So it's possible that my key might be wrong. So you asking me, hey, I think this is a better answer, that can help me identify an error that I made in creating the key or writing the test. Also, if you can give me a convincing explanation about why your answer is better, I'm willing to give points for that type of thing too. But you have to convince me.
Do you know when the test will be?
It should be up today. And I'm planning on giving you guys till next Wednesday to finish it. And also I'm gonna let you guys go back to the 3rd quiz and redo that if you've already done it, since the reading wasn't up. So you'll have that opportunity as well.
Do you want to go
That's why I haven't posted the quiz for you. Sorry, Tori.
No, you're good. Do you want to go over again the graphs for? Okay, actually, it's question 7 on the second quiz. About what graph to use when.
Okay.
Do you want to just go over again for something like that you would use for that? Like in a way that you would be asking the question for that? Do you want to just? Is there like a bullet point way to be like these graphs are for some extent?
Yeah, I'm not so sure I'll be able to whip out a question that I'm likely to ask on the exam right now.
Well, just,
whipping out a question is kind of hard, but yeah, we can absolutely look at the different graph types and talk about when they're more appropriate or less appropriate than the others. Was this about something that we were just talking about?
It's about some of the readings. It's a more personal one. I'm having problems still accessing reading 3.
It's because it's not up yet.
No, still.
So it should be, reading 3 should get posted today, and then the test should get posted a bit after that. So either a couple hours after the reading goes out or tomorrow.
The test covers up to reading 3, quiz 3, and that's it.
Yep, reading 3, quiz 3, that's it.
But reading 3 is
So what?
Reading 3 now.
I'm sorry, not reading 3, but the readings for week 3.
No, I mean reading number 3. I still.
No, reading number 4.
No, I'm saying reading number 3. I can't access.
Oh, come see me after class if you've got time, and we'll see if we can get that, because it should be up.
It is, it's just,
You can't get it.
for some reason, it's not great. I don't know if it's my computer, I tried doing it on different computers.
All right, see me after class and I'll hook you up. Okay, so different graph types. We had histograms, bar graph, line graph, and scatter plot. So histograms are typically used to show the distribution of a single variable. So let's say I want to plot the heights of individuals in this class. So I would have something like number of students, and then I would have heights, I don't know, from 5 to 4'8". I'm not sure if I do that right, all the way up to, let's say, 6'4", which I don't think we have anyone that tall. And then there would be little bars that would indicate how many people have the different heights. And all of these bars typically are about the same, well, they should be the same width, but my drawing stinks. So the histogram will allow us to see exactly how some data are distributed. Maybe we could go out further. We've got one really tall person. So this lets us very quickly see or get an idea about what the mean is. So if we looked at this, I guess the mean would probably be around here. And we also have a sense of how tightly packed things are around the mean. So we're also able to get a rough idea about how what the variance is. When I plotted things like this, basically these sort of represent like little histograms with infinitely tiny bars to represent how many people are falling at these different levels. And here you have a lot of people, and here you have very few. And when we're talking about the sampling distribution of the means, we're not talking about individual people, but like individual means in that sense. So these are sort of like a histogram, except not with the discrete bars like this. In addition to looking at frequency instead of using like the number or count, this might also be something like a percentage or proportion. So we basically have one variable on the x-axis and then just the count, the number of observations that we have for some other variable. Does that make sense? Now a scatter plot is related to the histogram. So a scatter plot, we get to see the distribution of observations in 2 dimensions. So this is just 1 dimension. How many people have this height? How many people have some other height? And you can imagine that if we plotted the scatter plot and we cut off a height, I'm not indicating a height of a bar here, but like I could count, okay, there are 1, 2, 3, 4, 5, 6, 7 in that group. There are 2 over here, something like this, right? But at the same time, not only do I know how the values are distributed on X, I also know how the values are distributed on Y, right? So if I wanted, I could create a histogram and count up 1, 2, 3, 4, 5, 6 would be in whatever this value is. If I replot, you can imagine shifting that and then counting the heights like this. But this also will give us a sense for where the mean is. So if I have something like that, let me back up and take a look. So it looks like the mean is right about here. And we also get a sense of how the variables are distributed both for the independent variable and the dependent variable. So in which variable do we have more variance? Sort of a trick question. The dependent variable. So in terms of the dependent variable, like imagine that we drew a line through the dependent variable mean. To see what the variance is there, we would just look at all of the deviations from that mean, right? So the dependent variable has a ton of variability. Says the dependent has more. Who says that, okay, I'll put you in there too. Who says that independent has more? What?
Which one, what is it?
Which one's the independent and the dependent?
Independent should be on the bottom.
Independent on the bottom, dependent up here, right? If you think about a formula in math, we have something like y equals 2x plus 3, which tells us how that line should look, right? So y is dependent on x. If x is 1, then y is 5.
Do they have the same amount of variable because there's the same amount of points?
There's the same amount of points, but variance describes how spread out the points are around the mean. So if we look at the points and how far they're spread out, imagine, like, we're basically, if we want to look at the variance for the dependent variable, imagine we squish all these together because this variable is really meaningless, right? So basically all we would do is we would get the difference between each of the dv values for the mean of that dv. Right? So let me do another one. So if the mean was there, well, we have a deviation like this here, one like that, small one, small one, small one. Holy crud, it's huge. So if I had to pick, if I was forced to choose which has the greater variance without any more information, I would say that there's more variance for the independent variable. Now the reason I said this is sort of tricky is because I don't know what the scale is. So imagine that this was like 1,000 and this was 10,000 and this was 1 and this was 10, which has greater variance, right? This would now have greater variance just because the scale is much bigger. So that's how it was tricky, which is why it's important to indicate what your scale is on the graph. All right, so that's scatter plot. You can see the distribution for 2 variables instead of just 1. It's also very useful for figuring out if there's a relationship between the variables. It's a little hard to see right now, but if I were to put a line of best fit through the data, it would look something like that, where as we increase in the independent variable, there's on average an increase in the dependent variable. So what type of correlation would that mean there is? A positive. Is it perfect? No, it's an imperfect relationship. Good. All right, so that's our histogram, and our scatter plots are bar graphs and line graphs. So this is one variable. These are all 2 variables. So bar graphs are like histograms in the sense that they have bars. However, oftentimes they are represented with gaps in between the bars. Why is this? Well, if you think about the histogram, when we had something like this and we're talking about height, you can have people that are 6'1", we can have people that are 6'1 1/4", 6'1 and 100 and 200 or 256. We can keep breaking it down into finer and finer gradations. So it's continuous, right? So we talked about continuous versus discrete variables, and one of the types of discrete variables were categorical variables. So if we were talking about something with 3. I'm going to make it simpler. Or whatever, yeah. So we've got Republican, Democrat, and other on some dependent variable. Now, we don't always have to have the separations here. We might have something like that looks sort of like a histogram, but it could indicate something different. Imagine that this is study time. And what would this be?
Score.
Yeah, sure. Score on some exam, right? Here, study time is also a continuous variable. We could have an hour, we could have an hour and a half, we could have an hour and 57 minutes, an hour 57 minutes and 2 seconds and 38 milliseconds, right? So we can keep breaking it down so we can connect the bars together, because really there's this, this continuation of the variable.
So then what separates that from the histogram?
What separates this from the histogram?
Two variables.
That's right, we've got two variables. Here we have study time, and here we have score. Now you might argue that, like, well, frequency is a variable too, and I would say, yes, okay, I'll give you that. However, with a bar graph, we can look at scores, we can look at almost any variable that you're interested in that has some continuous or some quantitative scale over here. Whereas with the histogram, usually we're just looking at frequencies or proportions. Okay. Line graph. With a line graph, in order to really be justified in using a line graph, you have to have the independent variable that's not categorical. Preferably, it would be something that's continuous. Because if you think about lines, right, the idea is that I can put in any value for x here and solve for y. So if I don't have a continuous variable, I'm not really justified in drawing a line. Now, anytime that you can use a line graph, you could create a bar graph. So let's say that this is a number of Facebook friends. Actually, Facebook friends, and the independent variable will be time, and these are females, and these are males. We could easily create some other type of distribution. So imagine instead we wanted to indicate male, female, we really only had 2 data points. Boom, boom, something like that. Does that make sense? Anything else?
Okay, Psych's difference between extraneous and confounding because they make that.
Okay, concise, that's the trick, right? So extraneous is any variable besides the independent variable that could affect the dependent variable. A confounding variable is an extraneous variable that is correlated with the independent variable. That's it.
There can be multiple confounding variables.
There can be. Yep. And although this isn't for the test, if you don't use random assignment in an experiment, you're guaranteed to have some confounding. Did you not get that? Did I get that?
Yeah, the first one.
For extraneous, extraneous is any variable besides the independent variable that could affect the dependent variable. Got it?
Yeah. I was just trying to, I still have a problem with like the difference between confounding and extraneous with the way you said that.
The only difference is that,
Correlates, doesn't it?
yeah, with the extraneous variable, an extraneous variable may or may not correlate. And what you want to do when you're designing an experiment, or even if you're doing a correlational study, is you want to correct for any correlations or eliminate any correlations of the extraneous variable with the independent variable.
So
Because if the extraneous variable is correlated with the independent variable, it's confounded.
So a confounding variable is always extraneous.
That's right. Every confounding variable is an extraneous variable, but not every extraneous variable is a confounding one. Yeah?
Nominal versus versus ordinal.
Nominal versus ordinal. Okay, so nominal basically means that there's a difference between groups or classes, categories. This is why it's also referred to as categorical. So anything where things can be grouped together or classified in a way that doesn't necessarily logically progress from more of something or less of something is going to be a nominal or categorical scale variable. So think about types of cars. There are Toyotas and Fords and Chevys and BMWs and Porsches, right? And lots of other types too. And you can group these things together, but it's not like, oh, well, this is more than that is, and this is more than that is, necessarily, right? I mean, even if you want to think about, like, oh, maybe BMW is a bad example. I was going to say, like, there's a difference in cost oftentimes between, like, some cars. But you can think of a brand that might be a bit more expensive on average, but the cheap of that expensive brand might be less expensive than the souped-up model of the cheaper brand, right? So there's not really a good way to order things in that way. Ordinal, on the other hand, has a natural order to it. So I don't want to say the wrong thing and mess up interval and ratio scale, but if you think about it, interval and ratio scales, they all have order, right? 2 is bigger than 1, 1 is bigger than 0, 0 is bigger than -3. However, what differentiates an ordinal variable from the other scales that are also, or that also have this property where there is this natural ordering to them, is that an ordinal scale, the differences between a 1 and a 2 aren't necessarily the same as the difference between a 2 and a 3. So if you think about, I don't know, races. Has anyone been in like a 5K or anything like that? So, like, I remember when I was in high school, and I was in cross country for 1 year because I just hated it so much. Although not enough to quit the team. So I remember, like, at a lot of the meets, there would be one person. The person that would come in first oftentimes would be like very far ahead of the people that came in next. Right? So the difference between 1 and 2 could be several seconds or maybe minutes or longer. And then you start getting into the pack. In number 27 and 28, yeah, 27 was faster than 28, but maybe only by a fraction of a second, right? And then you get to the slowpokes like me, and the difference between me and the person who came in front of me was often seconds different, or minutes, right? So there's an order. First is faster than second, second's faster than third, but you don't know how much faster the first was than the second, and the second than the third. You know there's more, but not necessarily how much more. Does that make sense? Whereas with the next scales, we do know how much more. There are 3 degrees more. There were 10 seconds more. Don't.
Is there going to be mathematical stuff on the exam? That makes me some hope that there might not be.
I'm not going to ask you to do anything in R. So in the week 3 reading, I'm going to go through some R stuff, and then you can go along. I show you how to install R in RStudio, or at least tell you where you can download it, and briefly walk you through the process. And then I talk about how to compute correlations and how to compute means and medians easily. And it was my original intent to have a couple of those computations, but that's not going to happen. Is there going to be some math? Yeah, it's not going to be as complex as like, what's the formula for covariance? and have like the formula for variance and the formula for covariance and the formula for correlation, and then have you pick out one or the other. That said, you should know the difference between biased and unbiased or less biased estimates. Do you need a follow-up question with that?
Can you go over the formulas of like each specific thing I've gotten? They're not really examples, but just to rewrite the formulas for my time and brain.
All right. So the studio participation. Let's start with the first one. The formula for mean. What does it equal?
It's sigma
Mean of x. So sigma
x
x
over n.
over n. Beautiful. How about the formula for the unbiased estimate of the population mean?
Not mu or n?
Mu.
Oh.
Just n minus 1.
Well-
So, yeah?
Sigma in parentheses x, right? And then
So sigma in the parentheses. Oh, are you talking about like this I equals 0 to n type thing? Don't worry about that. Or was there something
I
different?
have it here is s squared equals sigma and then parentheses.
S squared, that's different. That's not for the mean.
Oh.
S squared is the unbiased estimate of the population variance. So is this right? The mean? Tori, what did you say? Can you say it louder?
Should just be over.
Oh, you don't know. It should just be over n.
No.
No? No? Dan?
No, not all.
All right, well, despite the hesitation, I'm going to take your I don't know. It includes the word no, although it's a homonym and not the real word no. I'm going to take that as a no, and I'm going to take your answer, and that's absolutely right. It's the same thing. We don't have to make a correction for the mean. The mean in that original formulation will give us an unbiased estimate. We use this different notation to indicate that this is an estimate as opposed to the true population mean if we had access to everyone, right? So this lets us know it's an estimate, but the formula is exactly the same. Okay, so there are our means. And the next thing is, let's do variance. So sigma squared equals, so this is population variance. I'll give you a hint. It starts with a big sigma. It's a sum of stuff. What stuff is being summed?
X minus squared.
X minus the population mean squared.
Are we doing population mean?
We're doing population variance because we have the Greek letter.
Over n. Over n.
Over n. Still some more. Yes, that's right. So if we have the unbiased estimate of the population variance, what does this equal? It also starts with sigma. It's the same. So let's start off with the same. That's the same.
Okay, is that minus 1?
In minus 1.
That one's got this one.
One more difference. What else do we need to change?
Instead of doing m, there's an
Right.
x.
Yes. It's a sample. We don't know the population mean. We're estimating the population mean. So, but other than that, it's exactly the same thing, right? And if you think about it, really these are representing the same thing, the population mean, except the one we actually have and one we're estimating. So we took a sample. So, those are the formulas for the unbiased estimate of, or the population and the unbiased estimate of the population variance. And now we can talk about standard deviation, which is just what? So this is the population standard deviation. Sigma x minus m, or mu. Okay.
N,
Over n,
and it's over that, whatever it's called,
that thing.
Root.
Square root.
yeah.
That's it. Oh man, you had it. You had it. Right? I mean, yeah. So how about this? This is not an unbiased estimate, but it's the standard deviation that corresponds with the unbiased estimate of the variance. And this too, it's just the same thing. Let's take the square root. That's it. Were there other formulae that we needed to cover for this one? Covariance. Oh, right, because we're doing correlations and covariance on this one as well. All right, so covariance, x, y. How do I want to do this for the population form? Let's just say pop. I'll put P, pop covariance. What's that going to equal? It's going to equal a sum of some stuff, and there's going to be something over it.
Oh, is it like the sum of squares of x times, no, not sum of squares. Some, s of x and s of y at bottom, right? That's not it.
No, that's not on the bottom.
Basically, something.
But that is on the bottom for something in the future that we're going to talk about, so keep that in mind.
Brahmas.
So what is it?
Two sets of parentheses,
You
right?
need two sets of parentheses. Beautiful, good.
X minus the mean of x.
X minus, and this is for the population, so mu, and
Y minus mean of y.
y minus the mean of y.
Over n minus y.
All over n minus 1, is that right?
Yes.
No.
Oh, wrong. And then.
It's for the population,
Oh, it's just
Over n.
just over n. Great. And how about how about the estimation, the unbiased estimation of the population covariance?
it's the same, just n minus 1.
Same thing, almost. Yeah, it's the estimate, right? And y minus the estimate for the mean of y, all over n minus 1 as you indicated. That's it. Simple, easy peasy. What does the covariance mean? So does it mean how much two variables go together, or does it mean how well two variables go together?
I know that wrong, so I don't know.
See, I was hoping that you'd get it wrong on the quiz and look at the answer and then you memorize.
I think that
Right.
teammates, so I didn't like, you know, sink in.
Get past the anger, just like
I don't-
with the Force. Think about Star Wars,
I
right?
think
So
more.
you let that anger get in the way, it's gonna mess up your ability
My anger
to
fuels
follow
me.
the right path.
Anger fuels me.
You're on the road to the dark side.
I've been there. From Vegas.
How much or how well? How much? This is basically how much those two variables vary together. Now the next formula tells us how well. How well. And we create the next formula by comparing how much the variables go together with how much they could go together. So, this one I can write. So this is the Greek letter rho, which I don't actually have in the study guide, but we can talk about it since we're doing all the population stuff here. So this is the population form for the correlation. So it's the same thing as the sample estimate of the correlation, just with different symbols. So what is it? Or maybe we can start with R, because maybe you guys will have some of that. So correlation of R, for the correlation correlation of X and Y.
Equals the covariance of X and Y divided by
Covariance of X and Y divided by,
S of X and X of Y.
yes!
What is S mean again?
S's are standard deviations. When you have it squared, that's the variance. The unbiased, that's the population variance. Okay, so if we want to transform this into population form, let's transform all of this stuff. Just keep it the same, but yeah, whip out that cell phone. So how do we transform that into the population equation? I'll start with this because I just made this up. I'm sure there's some symbol for it, but I don't know what it is. X, Y, beautiful, all over what? So what's the population form of those? Woo! Do you want one? No. No. What is the population?
Oh, sigma squared.
There we go.
Yay.
Well, but not squared.
Just keep secret here, try.
Do we have a square over here? No, what do we have?
Random line, looks like that. Just not that. Okay. Multiplication.
Yes.
Oh,
Is there an X?
That's multiplication.
I'll just put it in parentheses and the next one in parentheses.
I want to get rid of that time. So, okay.
times X and Y.
What?
Times X and Y.
No.
I don't know.
It's hard. It's really confusing. Oh my goodness.
Oh.
Oh!
I'm
Oh!
done. I'm done.
Right? These are the estimates of this. I like that, the head nod. Yeah. I'm like Dr. Dre.
Oh my.
I get people's heads bobbing, but for a different reason.
Oh,
Da 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 da. It's the K to the N-A-double-P. What up, Mother Chunka? I can't swear in class.
That's why I can't go into public education, so I want to support.
You can in college. I mean, I can swear in college. It's my academic freedom. And in fact, I will swear if the situation calls for it, or I have a really fun class. Yeah.
What's the circle thing?
Circle thing. Circle thing. That's the small sigma.
Small sigma.
Small sigma.
Lowercase sigma.
Yeah. That's big sigma.
Okay.
Oh,
Yes. Go ahead. She's been asking me a ton of questions. I'm tired.
can you go over the build methods stuff again?
Mills methods. Yeah. 5 minutes of Mills methods. Oh boy. Maybe I won't even write stuff up on the board. So, the method of agreement. The whole idea is that everyone that you have has some, I don't know, some phenomenon associated with them, some outcome. They're all sick. They're all geniuses. They're all whatever. And you want to know what's the cause of the sickness, what's the cause of the genius, what's the cause of the A's on the tests. And so you look at all the things that the individuals or the schools or whatever it is that you're observing, and you look for something that they all share in common. So imagine we're looking at people and they had different breakfasts, and they had different upbringings and different political affiliations, but all of them studied more than 8 hours for the test. Okay, well maybe studying more than 8 hours is, the cause of getting an A on the exam. Okay? So that's the method of agreement. You You're looking, everyone has the same outcome, and you're looking for the one thing that's in common with all those people. Things get messed up or confounded if you have multiple things that all line up, right? So if they all studied 8 hours and they all happen to be on the football team, maybe you say like, well, is it being on the football team that allows you to succeed in my class? Which very well might go Mountaineers. Or maybe it's their study. I don't know. Okay, so the method of difference. There's a difference in the outcomes. So some people succeeded, some people failed. You're looking for the one thing that's the same in all the people that, that succeeded, but is different in those that didn't. So in this situation, maybe you have 3 people got A's and 3 people got F's. And, oh, the other thing. Everything about all these individuals is exactly the same except for the one thing that differs. So all of them are members of the same fraternity, all of them had 5 passed blue ribbons the night before the exam, all of them got 3.5 hours of sleep, all of them had the answer keys, but only 3 of them actually passed the class. And the difference between those 3 and those that passed and the ones that didn't pass is that the 3 that passed studied 8 hours, despite having the key. Maybe they studied that key for 8 hours, I'm not sure. So then the method of joint agreement, or the joint method of agreement and difference is sort of where you have a mixture of the two. With the method of agreement, all the outcomes are the same. With the method of difference, all of the potential causes are the same except for one. With the joint method, you have differences in all the potential outcomes, potentially, and differences in all the potential causes, and differences in the outcomes. And you're looking for the potential causes that line up with those particular outcomes. So it would be exactly like my last example, except say that some are male and some are female. Some had passed roulette, beer, and some were teetotallers, right? So there's a difference, and you're looking for the one thing that lines up with the outcome. The method of residuals is when you know about what causes some effect. So you have someone who failed an exam, and they come up and they're like, geez, you know, I studied this amount, and I read the book, and I did the homework, and the this and the that, and all those things I know contribute to success, right? But they failed, so what did they do? And then I find out that, that they were high when they took the exam. Okay, that's why, right? We're looking for the one potential cause that we haven't already attributed to something else. The method of concomitant variations is basically as one thing increases, we notice a similar increase in the outcome or a decrease in the outcome. It's basically like a real correlation. Increases of one are associated with either increases or decreases on the other. The amount of Beano that you take, the less gas that you have. But if she takes enough Beano, she'll be all right. You had one more thing, is that right?
I figured it out.
Good.
I had it downloaded.
All right. We'll see you guys on Wednesday.